Hello, welcome to the video. In this video, we will be discussing designing higher order filters. So let's get started. And as visible on the screen, we always consider omega u by k as our omega loop, which is unity gain, loop gain frequency, or we can also say unity bandwidth frequency. So we know that in second order system, our transfer function, or let's say the loop gain, basically is omega u by k by s multiplied by 1 upon 1 plus s by p2, as our pole lies on p2. So this gives a delay approximately 1 by p2. We are aware about this fact. And the system is critically damped for p2 equals to 4 times omega u by k, or p2 equals to 4 times unity bandwidth, which is omega loop. And basically it introduces a delay of 1 by 4 times k by omega u. So for p2 greater than omega u by k, overshoot is tolerable. So yeah, these are all things were discussed earlier. So in ideal delay case with a time delay of td, our loop function is basically omega u by k by s into exponential of minus s td, which gives a delay of td. And when it is critically damped, for td equals to 1 by e times 1 upon unity gain bandwidth, or omega loop. And for td equals to, or not equals to, basically for td lesser than the values of half of k by omega u, the overshoot is tolerable. So these are all the findings we have discussed earlier analytically. And now we will look at L of s, which is a function of loop gain, the magnitude of loop gain, the phase of loop gain, corresponding to the above values, which we know are reasonably good, and then make the loop gain of any higher order system correspond to the same. So let's take the case of second order system, and we know the transfer function of our second order system is something like this, and it has its critical damping at P2 equals to 4 times omega u. So let's first consider this case and forget about this written in red color pen. So the magnitude at j omega equals to 1 if omega equals to the unity gain bandwidth, or the omega loop. So the angle or the phase of L is basically pi by 2, which is contributed by the integrator, and tan inverse 1 by 4, which is contributed by one of our pole, where omega equals to omega loop, and the phase margin is equal to pi plus the phase angle. And basically, when calculated for second order system, the phase margin comes to be 76 degrees. So let's see the body plot, and what does the body plot tells us about the system. So initially the RAM decreases, and when it hits the 0 dB point, or let's say the magnitude is 1, we have our omega loop frequency, a unity gain bandwidth. So at this point, where past this point, we will be having our first pole, let's say at P2, where omega is 4 times of omega u. So basically, at this point, we see a decrease or a change from minus 20 dB per decade to minus 40 dB per decade. And this is due to the pole occurring at P2. So when we look at the phase, so our phase starts from minus pi by 2, and at omega loop it starts decreasing. It gives a curve before very near to omega loop, and then it starts shifting to minus pi, from minus pi by 2, and at the point where our pole lies, so at this point uh, the phase is minus 3 pi by 4, and it decreases again and gets stable at minus pi. As we know, at each pole we get a phase shift of 90 degrees. So this is how it works. And at the point where we have our omega loop, so this point and from this point till minus pi, this gives our phase margin, which comes about to be 76 degrees. Now let's take a case where we can say that somewhat over a little bit of overshoot is okay for our system. So let's take the case where our P2 lies at twice of omega u. So at that condition, it's not ideal, but it's not a right approximation. But let's say that for ease of calculation or explaining the concept, the phase is tan inverse 1 by 2. So basically the phase margin comes out to be 63 degrees. So here our red curve, which basically shows us that this is the point where P2 occurs at omega equals to, at P2 equals to twice of omega u. So at this point, we know that the negative ramp, changes its minus from changes its fall from minus 20 dB per decade to minus 40 dB per decade at this point, like this. And its phase basically starts from minus pi by 2, and initially it starts lagging before the point of p equals to 4 omega, and it goes to minus 3 pi by 4 earlier, and then it again goes to minus pi. So the point where we have our omega loop frequency, so at this point we have our phase margin from this point to minus pi. So the phase margin comes out to be 63 degrees. So this is how our phase margin is plotted on the body plot. And these are some facts we can talk about our second order system. So just to cross verify, let's take a system with ideal delay of TD. So we know the transfer function is omega loop bias times this factor, and using this we will get a critical damping when TD equals to 1 by E times 1 upon omega loop. And we know the magnitude is exactly 1 when omega equals to omega loop, and the phase will be minus pi by 2 due to the pi by 2 due to the integrator, and 1 by 3, well, sorry, 1 by E radians is due to our time delay TD. So basically the phase margin comes out to be 69 degrees, and which is very closer to 76 degrees, which we had when we had one pole. So our body plot will basically look like, we don't have a pole right here right now, so it will go on decreasing like this beyond our unity gain bandwidth, and the phase also will go from minus pi by 2 like a ramp, and at a point of omega loop we can see a phase margin of 69 degrees. And let's say uh, we can tolerate the overshoot, and which will give us a limited bring in when in the case of TD equals to 1 by 2 times 1 by omega loop. So here again the phase margin comes out to be 62 degrees, which is almost similar to the case when we had one pole, and which came out to be 63 degrees. So we are doing this analysis just for the sake of cross verifying with our standard time delay and the time delay introduced by a pole. So again the ramp will start will be decreasing with minus 20 dB per decade or its rate. And at the point of omega loop, the phase will also be lagging likewise, but the point at omega loop, the phase difference, or like the phase difference from minus pi to the actual phase, comes out to be a phase margin of 62 degrees. So this states that a system with a phase margin near about 60 to 70 is safe to go. So now let's analyze a closed loop negative feedback system for two poles, which is a second order system, or basically a third order system. And let's say we have a transfer function which can be modified to this. So this is nothing but g upon 1 plus gh, where the loop gain is gh, and the poles will be at j omega axis, which is our boundary condition. Then the denominator is 0 for some value of omega. So let's say 1 plus 1 upon gh. As we know, gh, which is our loop gain, is equals to this value. So 1 plus 1 upon gh, after putting this value of gh, nearly comes to exactly this value. And we know that we want to evaluate it at some s equals to j omega, where our boundary condition lies and our poles will be at j omega axis. So we have to evaluate to s equals to j omega, and when we solve this value, or let's say this is a denominator, when we solve it, when we put the values of j omega, then we will get two parts, the real part and the imaginary part. And to let's say go for our boundary conditions, the denominator is 0 for some value of omega. So we have to equate our real part to 0 as well as our imaginary part to 0, as both parts must be 0 to achieve boundary conditions for our poles. So let's take our real part, and when equating to 0, we will get this equation, and same for our imaginary part, we will get this condition. And then substituting the value over here, we will get the condition where if P2 is equals to omega loop by 2, from this condition, the gain becomes infinity, or the poles comes at imaginary axis, which is j omega axis. And similarly, at that time, omega is basically omega loop by 2. So it is a frequency at which again the gain comes to infinity, or the poles, right, or occurs at imaginary axis j omega. So this means that there is a closed loop instability if P2 equals to omega loop by 2, or if P2 is greater than omega loop by 2, then the poles will definitely be giving us the overshoot or instability. So now to calculate where should the poles actually be in order to have no ringing, it is very complicated process. And the solution to that is basically we can ensure that the phase margin is equals to 76 degrees, which is derived from the second order, and we can implement it to any higher order. Let's say in our case, in this case, it is third order system. So based on the guidelines we got from second order system, if we compute our phase margin to be 76 degrees, we get P2 to be 8.1 times omega loop. And as we know, in our third order system, there are two poles. So one pole contributes to 1/4 of its omega loop time delay. So basically, two poles will be contributing 1/8 of the total time delay, and that's how we can state that P2 equals to 8.1 times omega loop. We'll get this condition after considering the phase margin to be 76 degrees. And similarly for higher order system with three poles, i.e. fourth order system, for stability we will get the condition P2 must be greater than 1.125 times omega loop, and P2 must be equals to 12.2 times omega loop for having 76 degrees phase margin. So for the system with 4 poles, i.e. fifth order system, for stability, our P2 must be equal to 16.3 times omega loop for having the phase margin of 76 degrees. To summarize for the things for higher order system, so let's take the order and its loop gain function L of S. So we'll consider the factors of is there any kind of instability and the condition where it is critically damped and the phase margin required for critical damping. So in our first order system where our loop gain looks like omega loop by S, there is no instability and there is no condition for critically damping, but its phase margin always is 90 degrees. In our second order system where our function loop gain function looks like this, there is no instability, it is unconditionally stable, where P2 lies at 4 times omega loop for critical damping, and in that condition we get the phase margin of 76 degrees, and we will apply 76 degrees to all the further higher order um, system so that we get declared stability in those systems. And when we apply this phase margin, then we reverse calculate, so we get the condition where our P2 should be at 8.1 times omega loop for the third order system with 2 poles, and for our fourth order system with 3 poles, we will get P2 equals to 12.2 times omega loop to achieve a phase margin of 76 degrees. So basically for critically damping. So this is how we make use of phase margin for the stability of higher order systems. So now let's take a look for the body plot for second order, third order, and fourth order systems where we have 1, 2, and 3 poles. So when we have one pole, one or two identical poles at P3, which is a third order system, or 3 identical poles at P4, which is a fourth order system. So a ramp will decrease properly and it will shift. So it will basically shift to even higher slope when we have higher number of poles. As we know, a pole introduces a shift in decrease of its function by minus 20 dB per decade. So this is how our second order system will behave. This is how our third order system will behave, and this is how our fourth order system will behave, provided that the poles will arrive at these positions where it is 4 times omega loop. As we know, P2 is lying at 4 times omega loop. Then we have 8.1 times omega loop, and we have 12.2 times omega loop. And the fall in slopes will be more for higher order systems, as we discussed earlier. Ignore this mistake of mine. And yeah, coming to the phase shift. So basically the phase shift and the phase margin. So phase margin is same for all the plots. So basically our first order system will give a phase shift of 90 degrees due to one pole, and of 180 degrees due to 2 poles. And furthermore, as we increase the order of our system, the phase lag will look something like this. But at the same time, our phase margin will be same, which is equated to 76 degrees. So when we look at our Nyquist plot, so we set the phase margin at this point, which is basically from this axis, which is 76 degrees. So now for our first order system, it will look like this. For our second order system, it will go from here, but from the same point. And for our third order system, it will go like this over here. So this is our Nyquist plot will look like, which will be clearly telling us that our system does not encloses the critical point, and thus it is stable. So let's generalize the concepts. So basically, for the higher order systems with the order of k, we have Ls equals to unity gain bandwidth divided by S times 1 upon summation of k equals to 1 to n minus 1. So for our nth order system, multiplied by 1 plus S by P k, and this is for our nth order system, where the magnitude will be 1 at omega equals to unity gain bandwidth omega loop, and the angle or the phase of our loop gain will be minus pi by 2, which is introduced by our integrator, and summation of k equals to 1 to n minus 1 tan inverse omega loop times p k for, and this is for nth order system, where phase margin is nothing but pi plus the phase of loop gain. So we usually want phase margin to be 76 degrees. So basically, if we want our phase margin to be 76 degrees, we want this portion to be 14 degrees. And thus we can calculate a reverse calculation. We can make reverse calculation for any higher order system, providing that phase margin is should be 76 degrees. So in terms of delay, the total excess delay is nothing but summation of k equals to 1 to n minus 1 upon pk is totally delay introduced, and this delay has to be limited to some reasonable amount in order to make our system stable. So this can be either a case where we have 1 by e times 1 upon omega loop. So this is the case for strict critical damping, and the total access delay should limit it to this case, or maybe we can say that it should be lesser than this condition or this value for the condition of critical damping, or let's say we can tolerate some kind of overshoot. So let's say 1 by 2 times 1 upon omega loop is a case where we have ease of overshooting. So our total access delay should be lesser than this value or limited to this value. So we have generalized the concepts of phase margin and Nyquist plot for higher order system. And I think that's it for this video. Thank you for watching.